Thank you for attending my talk today. I will be happy to present our latest finding on smart post-oxidation of FNC brake rotors, an innovative technology to enhance corrosion and braking performance. My co-author is Carl Michael Winter, the VP of our R&D department. The motivation for starting our development was the announcement of the new and strict regulations for Euro 7 standard. So to reduce the particulate matter emissions for commercial cars. So to comply with these limitations and regulations, we need first to explore the potential factors that are contributing to particulate matter emissions, including brake and pad materials, and then figure out the required solutions. We know that the gray cast iron is poor in corrosion resistance, so once the rust forms, if it's not removed, it will build up and accumulate, generating excessive noise and vibration, increasing the stopping distance and brake pad frictions, and so on. So once the brakes are engaged, they will release a huge amount of particulate emissions. So the focus was on developing more corrosion-resistant brake rotors. For this purpose, different technologies were used, including laser cladding, cold spray, which are very expensive. If we use a carbon ceramic to replace the gray cast iron, it is also very expensive and it has less heat dissipation. Using a conventional conversion coating to a gray cast iron, it's less expensive but gives just moderate improvements. So Ferritic Nitrocarburizing is the most cost-effective and easiest solution. Using FNC on brake rotors, it's a proven technology. It was used for the first time by General Motors. They were able to find that they increased the service life from 40,000 to 80,000 miles. They reduced the brake wear and the pad wear. They reduced the pad friction, and this was confirmed by other different studies. One of them is presented here. And they enhanced the corrosion resistance, but I should note that with using only ferritic nitrocarburizing is not, it will give just a slight improvements as demonstrated here in this picture for a FNC treated sample. After 22 hours, there is a lot of rust that it forms. What is ferritic nitrocarburizing? It's a thermochemical treatment that involves introducing nitrogen and carbon into the steel surface at elevated temperature, between 500 and 600 degrees centigrade, to enhance the performance of the steel compounds in terms of wear, corrosion, hardness, and fatigue, and so on. During the treatment, it forms a compound layer that is composed of an epsilon and gamma prime, and underneath it forms a diffusion layer that is composed of alloying elements, nitride and carbide, and it can achieve up to 275 microns as an effective case depth. And on the top of the compound layer, we can apply an oxide layer that it will improve the corrosion resistance. FNC is gaining popularity. The FNC treated rotors vary for the specifications from manufacturer to other. So Nitrex has developed new generation of FNC ONC rotors that used an advanced control system, which include this Nitrex SGS hydrogen analyzer that allow us to obtain a compound layer with different thicknesses, chemical composition, and porosity, and an oxygen probe that allow us to control the post-oxidation to obtain the highly corrosion resistance magnetite layer. And this presented here on the right, they are typical surfaces that we can obtain. Prior to FNC, it is mandatory to apply a stress relief process to remove all the internal residual stresses that can happen during machining and casting. The temperature of the stress relief should be set at 30 degrees above the FNC temperature. And after stress relief and FNC, the hardness and the shapes of the rotor will remain stable. To evaluate the corrosion resistance, we performed salt spray testing according to ISTM B117. The results show that the untreated gray cast iron is completely corroded within 24 hours, and the FNC only treated sample was surviving 40 to 60 hours, but when applying a controlled post-oxidation, the corrosion resistance was enhanced. And we can explain this by scanning electron microscope. The SEM images shows that there is some porosity on top of the compound layer, especially near to graphite flakes. And if we apply a post-oxidation, the oxides will fill the pores and form a thin top layer that enhances the corrosion. To further improve the corrosion resistance, we developed Smart ONC, which is an in-furnace controlled post-oxidation that contains a chemical agent. With scanning electron microscope cross-sections maps, we can see that we have formed a compound layer with about 20 to 30% of porosity, which was controlled, and it contained metal 1, which is the Smart ONC chemical agents. And also a continuous and compact oxide layer that contains also the metal 1. With the chemical composition done by electron dispersive spectroscopy, we can see that we have a compact and homogeneous magnetized phase, which contain 2.7% atomic of Smart ONC chemical agents. And the local high concentration shown on the picture B indicate that the micropores was filled and sealed with the metal 1 oxides. To compare the behavior and the performance of ONC versus Smart ONC, we did additional corrosion testing. The ISTM salt spray testing shows that the ONC starts corroding from the heads after 48 hours, and it's quickly spread. While for Smart ONC, we can see that the first spot appears after 216 hours, and it doesn't spread even after 340 hours. And we can also see that there is a significant improvement in the ventilated area. We did also cyclic corrosion according to SIE G2334 standard for full rotors. After 36 cycles, we can see that Smart ONC is behaving much more better than ONC. To compare the different type of failures and the coating quality, we performed scratch testing on both the ONC and Smart ONC. The different type of failures that we can observe on the FNC ONC, it includes tensile fracture, lateral fracture that happened on the side of the scratch, and the adhesive failures that involves the removal of the oxide layer. The scratched sample was put in salt spray. After several hours of exposure with the scanning electron microscope, we can see that there is visible corrosion that appear on the scratch and around it. And with chemical analysis, we can see the existence of nitrogen and carbon, which indicates that the oxide layer was removed and the nitride layer was discovered. While for the FNC Smart ONC, it shows superior protection against these failures, which indicates an improved performance. We tracked also the behavior of Smart ONC scratched sample in salt spray before and after. We can see that after scratching the sample and prior to putting it in salt spray, the deepest area at 5.5 microns shows the presence of oxygen and metal 1. After several hours of exposure, the scratch was almost completely covered. The deepest area in the red box, it's still under self-healing process, which was shown by high magnifications of SEM on the left-hand side and confirmed by chemical composition, which shows that we have metal 1 oxide and we note the absence of nitrogen and carbon. So what's happened during salt spray? After scratching the sample and putting it under humidity, the Smart ONC coating elements was dissolved, and the dissolved ions was diffused from the composite coating to the scratch to recombine and form a non-soluble coating that covered the scratch. This process of self-healing is progressing over time. For the evaluation of the tribology properties, we did dyno testing according to SIE 2707B on an untreated disk and two different variants of Smart ONC with high and low carbon on the compound layer. Using neopads, these tests include 9 steps and different highway blocks with high speeds. The results show that the stopping distance was not affected by applying FNC Smart ONC. The figure 1 shows that the untreated gray cast iron is showing the highest coefficient of friction. The Smart ONC starts lower but matched the value of the gray cast iron after the highway block 2. Figure 2 shows that the pad discs was not changed, which indicate that there is no change in the thermal properties after applying FNC Smart ONC. Figure 3 shows that the highest value of pad temperature was obtained on the Smart ONC variants until the end of the highway block 2. And there is a consistent rise of pad temperature to achieve the bending temperature at about 200 centigrade. It was achieved first for the high carbon one and then for the low carbon one, which indicates a change in the surface friction by the pad material pickup. The comparison of the different discs after dyno test shows that there is appearance of the grooves on the untreated gray cast iron, while for Smart ONC variants, there were no grooves, no wear, no cracks that appear on the friction surfaces. And for the pad, there is a few wear and no visible cracks was observed. And on the Smart ONC variants, we have material accumulation on the friction surfaces, especially for the high carbon one. All the treated samples, they exhibited an average compound layer of 19 microns and 2 to 3 microns of oxide layer. The hardness of FNC is between 800 and 700 Vickers. After FNC Smart ONC, the thickness and the rotor roughness was increased, and the high hardness obtained after FNC was decreased. After dyno testing, the roughness of all discs was decreased to achieve a value about 0.3 microns, and the rotor thickness was decreased also for all discs. The micrographs of cut samples on the friction surfaces reveal that the compound layer was not worn off after dyno test. Contrary to expectation, the thickness of the compound layer still the same before and after testing. And we can see that there is no cracks, no delamination, and no pores that appear on the compound layer. In addition, there is appearance of a thin top layer that formed on the compound layer, which is due to material transfer film from the pad to the friction surfaces of the discs. We did also electrochemical corrosion testing to compare the performance of the corrosion resistance before and after dyno testing. The trend of the Tafel curves shows that the untreated gray cast iron, yellow one, is the worst, present the worst corrosion resistance, which improved slightly because of the burnishing. And the Smart ONC variant shows a corrosion potential that shifted on positive values. The low carbon variants, the green one, show the highest corrosion resistance, which was decreased after dyno testing because of material loss from Smart ONC and the high carbon variants shows higher corrosion resistance compared to low carbon variants after dyno testing because of the thin top layer that formed from the friction surface, from the pad material to the friction surfaces, which act as a protective layer. So as a summary, the Nitrex smart solutions include controlled processes that provide us with a controlled diffusion layer, oxide layer, and compound layer with different thicknesses, chemical composition, and porosity that can help us to meet almost all the requirements. And the Smart ONC, which provides superior corrosion resistance up to 200 without any spots. Adding to that, there is the self-healing properties that cover and repair the damages that can happen on the surface, and the superior protection against any failures. It eliminates the need of zinc-rich paints, which reduced highly the cost, and it provides a full coating with uniform thickness throughout the parts, and it improves also the thermal stability, which is up to 600 degrees centigrade, compared to the zinc-rich paints that maximum that can achieve is 400 degrees centigrade. In addition, there is the fully automated multi-chamber continuous furnace, which is a unique machine that Nitrex has developed for mass production. We can apply FNC and stress relief in the same chamber, and we can load up to 3 metric tons in the same load. For more questions, we can explain this in our booth. Thank you so much for your attention.